Okay, so hello everybody. I'm pretty happy to be here, and thanks for giving me the opportunity to give that talk. So I added neutron star on my title because I think they are also very important in my field. And I'm not going to lie, I don't know anything about microlensing. I'm not an expert about deriving the mass of black holes and neutron star. My expertise is rather trying to understand how galaxies are evolving, how the stars are evolving, and how the chemical elements like carbon and oxygen is evolving and is mixed in the gas inside galaxies, which all relates somehow to neutron star and black hole, which I will describe that in a moment. So hopefully this will be a very refreshing talk. It's going to be different. You will learn a lot of things, but it can also be the worst talk of the day. Nobody will understand what I'm saying, and it's going to be just a pure catastrophe. So I will try to be somewhere in the middle. I guess I can change slide. Nice. Okay. So what is galactic chemical evolution? That's the evolution of the elements inside galaxies. So you start by having gas inside a galaxy, here the Milky Way, and then this gas, because of gravity, is going to collapse. It's going to form stars, and stars are going to create new elements through nuclear fusion. It's going to create oxygen, titanium, and these sort of elements. And at the end of their lifetime, they're going to either explode or release material through stellar winds. So when this is happening, most of the element that has been produced by stars is going to be ejected back in the gas near where they form. So when this happens, you have a gas that is now more enriched in new elements. You have more oxygen, you have more nitrogen, and then this enriched gas is going to collapse once more to recreate the cycle. So as you move forward in time, you get more and more elements into your galaxy, and then your gas is getting more and more enriched. You have more and more of these nice elements that are created inside stars. So in the jargon, we say that the metallicity of the gas is increasing as you move with this cycle, and I'm going to say metallicity a lot during my talk, so I think it's good to have a recap of what this actually means. So that's the periodic table from the point of view of nuclear astrophysics. So you have the number of neutrons here, the number of protons, and this is showing all the elements that you can have, and it shows all the isotopes and the stable ones and the unstable ones. Now, from the point of view of a chemist, you see something more like this, and you have noble gas, you have metals, but when you're in astronomy, you're actually looking at something that is much more simple. So you have hydrogen, helium, and metals. So when we say metallicity, we basically mean the concentration of all the elements that are here compared to the total mass of your gas. It seems a little bit ridiculous, but I think there's a historical reason for that. So at the beginning of the universe, you only had hydrogen, helium, a little bit of lithium, and basically all these other elements has been produced in stars. So measuring the metallicity is a measurement of how efficient stars have been producing elements throughout the lifetime of the universe. Now, I'm not just showing this because it's a nice joke, but it's also because I want to remove the impression that astronomy doesn't care about elements. We often say metals, metallicity, but we do care about individual elements, and this is one of the main goals of the field of galactic chemical evolution. When you go a little bit deeper in this subject, you realize that stars are not producing the same elements. So, for example, massive stars, they're going to create a lot of oxygen, a lot of magnesium, and when they explode, they're going to produce a lot of calcium, titanium, and iron. Different type of supernova explosion that are type 1a are basically a white dwarf coming from the remnant of low mass stars. If it managed to explode, it's going to create a lot of iron, a lot of manganese, but not that much else. And then you have low mass stars like our sun, a little bit more massive. They're going to produce elements such as nitrogen, carbon. That's where most of the carbon in the universe is produced. And also exotic elements such as strontium, yttrium, barium, which I'm not sure you care about, but these are elements that they are producing. It also produces lead, which is an element that probably most of you, well, everybody knows lead, right? And then neutron star mergers, which is a little bit more exotic. If you merge two neutron stars together, you're going to produce what we call the rapid neutron capture process. And this is half of the heavy elements that are more heavy than iron are produced throughout this process, and you're going to create gold, silver, and europium, and these sort of elements. Now, coming back to the life cycle of stars, you start to realize that it's becoming a very complicated mixture, because once you do a couple of life cycles, there's many stars that are going to contribute, but each of the stars is going to put their specific chemical signature in the gas. So when you mix all that together, you get a very complicated mixture that you need to disentangle once you do observation. So bottom line of this stars obviously affect the chemical composition of your gas because they do produce the elements. But there's something a little bit more complicated because there are other stuff that are modifying the chemical composition of the gas, which has to do with how galaxies are evolving. First of all, you have galactic inflows. So you have a galaxy here that's a simulation, and you see these streams of gas coming inside the galaxy. So this is because of gravity, and this gas is going to fuel the star formation process. But the important thing is that this gas is actually having a different chemical composition. The metallicity is typically lower. So when you introduce this gas inside your galaxy, you're going to change the mixture of your gas inside the galaxy, and you're going to change your abundances. Another important process is galactic outflow. That's real observation. You have a galaxy disk here, and you see these nice outflows that are going outward, exciting the galaxy. This is happening when you have many supernovae that are exploding at the same time, and then you create this excess of energy, and then you're going to heat your medium, it's going to expand, and basically you're going to blow your material out of the galaxy. When this is happening, some of the element that has been produced in star and released in the interstellar medium is going to be ejected. So that means that these elements may not be recycled into new star. So this is actually exiting the system. So it's going to change your composition of the gas inside your galaxy. Now, to put a little bit more confusion, there is something that is called galaxy merger. So galaxies are formed in groups. They interact with each other, and you have two spiral galaxies, one here and one here. You can see gas that is flowing inside this galaxy, and because of gravity, they're going to spiral in one another, and eventually they're going to merge together. When this happens, you combine all the stars, but you also combine all the gas, which makes this very complicated because each of the galaxies, because they have different inflows and outflows history, they have different star formation history, the chemical composition of their gas is not the same. So if you merge that together, and then today you see one galaxy, which is this one, you have a gas composition that is the combination of having two different evolution history. And then you need to try to decompose that into whatever this is to understand how the system has been evolving. So the field of galactic chemical evolution is a field that englobes a lot of different fields of physics. And this is a type of plot that I'm going to show during the presentation, and it's probably seems pretty boring compared to the nice video that I've just shown. But this is a type of plot that we're working on in our field. So I think it's important to present you how this is working. So you're looking at stars in the Milky Way. Each of the cross represents one star that has been observed using spectroscopy. Because you use spectroscopy, you are able to know what are the different abundances in your star. So here is calcium over iron. We always do ratio in this field. So this is always a ratio of two elements that is produced by a star. So this is telling you how much calcium you have relative to iron in your atmosphere of the star. It is normalized to the sun. It's in log ratio. It's in the log space. So when you hit 0, that means you have the same relative composition that you would see in the sun. Now this axis is pretty important. This is iron concentration, so iron divided by hydrogen. We sometimes call this metallicity. Doesn't make too much sense, but that's how we call that. And so the important thing is this is a proxy for time. Because at the beginning of the universe, you don't have any iron. And because of the life cycle of stars, you're going to progressively put more and more iron in your gas, and then you're going to go from the past to higher iron concentration to the present here. So that means that these are young stars and these are very old stars. Now the important thing about stars is when they form, they're going to keep track of the composition of the gas in their atmosphere. Of course, they're going to create a lot of elements. The composition is going to change, but that's more inside the core of the stars. In the other layer, the composition is going to stay roughly the same. So that means if you go back in time and you look at stars that are older and older, you're going to probe the composition of the gas back in the past. So we sometimes call this galactic archaeology to look what was the composition of the galaxy at early times. That's the description of the plot. Okay. This is another interesting plot where we show calcium over iron and magnesium over iron just to show different elements. And now the black dots are individual stars in the Milky Way, and the different colors are different dwarf galaxies. So they are totally different systems. And the goal of chemical evolution is try to understand everything about this. So why do galaxies have different chemical evolution trends? First of all, where the elements are coming from, but also why fornax, for example, have lower calcium than the Milky Way. So this is something, to answer this question, you need to know how stars evolve, what is the nucleosynthesis, and how galaxies evolve. So, very big introduction, but I'm getting to black holes, so don't worry. So when you try to model this with numerical simulation, you need to account for this long pipeline. So you need to collect the smallest and the largest scales. It all starts with nuclear physics that provide nuclear reaction rates that are put inside stellar models. So these guys are reproducing the evolution of the structure of the stars. They follow the nucleosynthesis, the production of the element, and then they explode their model. And they provide what we call stellar yields. So this is a table that has all the elements and all the isotope that is ejected by stars. They do this for many, many stars, and then they give us to us, and then we combine that with different populations into the model code, and we have stellar cluster, and then we embed this into galaxy model to follow the life cycle of stars using their population code, and we can also include different processes with respect to galaxy evolution. So this is good because we can include a lot of different physics. We can create a coherent picture of how stars and galaxies evolve together, but that's implying a lot of uncertainties and a lot of degeneracies. Because this is the cumulative uncertainty scale, all relative, but if you are in a galaxy model, you of course have your own uncertainties. You know, you have uncertainties in your parameters, but you carry the uncertainties of all the model that precedes it, including stellar models, which are basically the foundation of every galaxy model that tried to address chemical evolution. Okay, so stellar models, galaxy evolution, weird isotopes, strontium, and gas floating into space, and all that, but what about neutron stars and what about black holes? That's pretty much why I'm supposed to be here. So I would like to show you how the mass of neutron star and the mass of black hole is actually affecting the way we interpret observation, and the way we try to understand galaxies using chemical evolution plots like the things I've shown you in the previous slides. So I would like to show you an example to highlight the impact of neutron star and black hole. So this is the relation of oxygen over iron as a function of iron concentration, or again, as a function of time. So all the dots are individual stars, and the line is the prediction from my model. So I would say that the fit is good. And people have fitted this relation many times, like for decades, they have been fitting this relation. And this is a sign that your model is well tuned and your model is behaving correctly. And therefore, you can conclude something about your galaxy model and learn about galaxy evolution. But this is actually having an assumption that is all massive stars between 8 solar mass and 40 solar mass produce an explosion and release a neutron star at the end. Even some people push this limit up to 100 solar mass, so everything explodes. So we know that below 8, it's not going to explode. It's going to produce some sort of AGB stars, like it's not going to produce the same elements, but that's the assumption. But now we start to be aware by observation, so that's a compilation by SMART 2015, where you have the initial mass of the star that has been observed to explode as a supernova. All these are detections, and they are sorted by initial mass, so that's why it's shifting a little bit to the right. And apparently, statistically, we have observed enough of these progenitor to claim that if stars more massive than 20 solar mass would explode, we would have seen that. But we have not, and that means that observationally, there is no good reason for why stars in this region will produce a successful explosion. So that means that they most likely collapse into black holes. So that means that I probably fit the data and I have the right reason, I have the right answer for the wrong reason. But that's okay, I have a model, I can say to my model, well, just let's fix this. Let's just assume that the stars between 8 and 20 solar mass explode and the rest just produce black holes. Well, I have this awful fit. Now everything is wrong and I'm starting to worry about what the hell is going on. And basically this is very puzzling because now we start to worry, where does the oxygen come from? Because if you look at the oxygen over iron ratio in the ejecta of massive stars, you realize that this is going up when you go to more massive stars. But if these more massive stars do not explode, well, you lose all your precious oxygen. So now we need another interpretation to be able to refit the observation, because somehow, because the data are there, it must happen somehow. And I want to show you how the remnant mass of stars can help to build a scenario where we can fit this relation. And for that, we need to go inside stellar models. So you don't need to understand all these lines. This is a 1D stellar model. So here you have the mass fraction of the element. It tells you how abundant each of the elements is. That's the surface of the stars, and you're going toward the center, which is right here. So you have the density profile, the temperature profile, and each of the line represent a different element. So I thought that was pretty confusing, so I'm just going to show you here what are the elements that are the most abundant in each of the layers. Yeah. Hydrogen, helium, oxygen, silicon, and iron. So in oxygen, you have also a lot of neon and carbon, but this is pretty much telling you that the classic picture is kind of true. It's more complicated, but at the end of the lifetime of a massive star, you have all the structure, you have an onion shell, and then you have different elements in each of the layers. Now it's the time to explode the model. What they do is they propagate a shock throughout all of these layers, and then this shock is going to change the temperature and the density. It's going to create new elements and all that. But at the end, they need to figure out how much mass is going to be ejected and how much mass is going to be kept and form the remnant object, which can either be a neutron star or a black hole. If it's a black hole, let's say a pretty big black hole, well, it's not very interesting because this star is mainly going to eject helium and hydrogen, so pretty boring. But if it formed a neutron star instead, now it's going to be interesting because you're going to eject iron, silicon, and oxygen, and many other elements. But what if the neutron star was slightly more massive? If this is true, well, you could have this situation where you will basically lock all the iron, but you will eject a lot of oxygen. So that is actually a quite appealing solution to solve this oxygen crisis. It's not too much of a crisis, but too late I said the word. But yeah, so if you want to bring this line up to be consistent with observation, since we cannot inject more oxygen, what we can do is to reduce the amount of iron here. So by reducing the amount of iron, you're going to enhance your ratio. So that's actually a pretty good theory, but it changed a lot the interpretation of where the elements are coming from. You came from a theory that the most massive stars were ejecting a lot of iron. Yes. Sorry? Oh, you mean these data points? Oh, that's actually a star. So it just tells you what is the surface abundance of that star. Yeah. And then we see that there's a lot of oxygen in these stars, so yeah. So yeah, exactly. So we thought that oxygen was coming from more massive stars, but then we noticed maybe this is not true. And on top of that, the star that we believed that was ejecting a lot of iron do not eject that much iron. So it changed a lot of our interpretation. But this is still a theory, and in order to make sure that we understand if this is correct or not, what we really need to know is the relation between the initial mass of a star and its final mass. Basically, we need to know that I give you a star, I have like a star of 15 solar mass, tell me if it's going to form a neutron star or a black hole. And if it forms a neutron star, what will be its mass? Because depending on its mass, it's not going to eject the same chemical abundance. So obviously, that is something that the New Grid collaboration, which is a group that tried to create a consistent set of stellar yield, start to be aware of this problem. So what they are currently using is the available mass distribution of black holes and neutron stars. So this looks like this. You have the remnant mass here, and these are X-ray binaries. So Chris Fryer came with a theoretical expectation of what would be the relation between the initial mass of a star and its final mass. And he plugged that into different models, and basically he ended up having this red line. So it's not a perfect match, but at least there's a clear gap in observation, and he was able to reproduce this gap using his model. Now, here's the thing I don't really like about this set of constraints. First of all, yes, that's what New Grid is using. I need to practice my timing here. The thing I don't like about this is that there's only 80 neutron stars and 20 black holes. So that's not significantly a big sample. That's not really a big sample. The other problem is this comes from binary that are emitting X-ray. So in order to compare this with observation, you need to take your theory about what is the mass of your stars and what is the final mass, and you need to convolve that into a population synthesis code that will follow the binary evolution of stars, the mass transfer, and all that. And when you're done, you just pick the one in your model that will have the same characteristic to produce these X-ray emission. So you don't have any direct observation. You need to convolve this into a very complicated model to make the comparison with a very low amount of stuff. So, of course, you can do something else with microlensing, and that's my connection why I'm here. We can do this with microlensing. So I'm not going to explain that much in details because I think everybody started to get it by now, but you have the source and you have the lens, and we see the Einstein Ring because of the microlensing effect. And what I like about microlensing is basically you just need something that has mass. You don't have to be in a binary, you don't have to emit you don't have to emit light. As long as you have mass and you are in the line of sight, you will be detectable. And of course, so the Einstein ring is dependent on the mass of the object, so if you know the distance, you will be able to detect the mass of the neutron star and black holes. Now, as we have learned, of course, we don't see the ring because we don't have enough resolution, so basically we can use the time scale to measure the mass. So that's the distribution of objects that can be seen by microlensing and WFIRST. And this is related to the time scale, which is related to the angle of the Einstein ring, which correlate with the mass. So that's why when we have longer time scale, you go from planetary object to neutron stars and black hole. And that is something WFIRST could observe and microlensing currently can do. And what I like about this is it's going to provide a sample that is less biased than what we are currently using to train our stellar models. You basically have, as long as they are on the way, you will be able to detect black hole, individual black holes, individual neutron stars, or a combination of binary black holes and all that. So that's going to help a lot define what is the actual mass function of neutron stars and black hole. So in this grand scheme, WFIRST and microlensing can actually help a lot to constrain the stellar models. More precisely, what amount of iron and what amount of oxygen is going to be released by these stars. If you better constrain this, that means that you help all this community, because the stellar model are the foundation of galactic chemical evolution. Now, as an exercise for the rest of the presentation, I would like you to take my shoes and try to analyze observation without taking care too much about stellar models. I want to show you how it's easy to derive conclusions about how galaxies are evolving just based on what we see with chemical evolution. And at the end, you will see that just by accounting for this uncertainty, well, you can kind of screw everything up. So the reality is that we have a lot of uncertainties in stellar model, especially for the iron yields, because iron is formed deep in the center of the stars. So if you change your neutron star mass by slightly a little bit, well, you will change a lot the iron yields. Okay, so let's go for the example. The example I've taken is the origin of our process element, so the rapid neutron capture element. These are very massive atoms, and for a long time, people have thought that core collapse was producing all these elements. But now, from a nucleosynthesis point of view, neutron star mergers are actually more compatible to produce these elements. So if this is true, well, here's the scenario. So we have, that's not what, yes, we have a laser. You have two massive stars, this is time, and then as a function of time, one is going to explode, you release iron, and then the other is going to explode, you release iron, and then you need to wait until the neutron star orbit one another, and then coalesce here, merge, and when they are going to merge, they're going to release our process element, going to produce europium, because in our field, europium is the tracer of the R process, and the remaining is going to form a black hole. Now, if this is true, well, we can try to model this to test if this is correct. So here is the same kind of plot, but you have europium over iron, and you have iron over hydrogen. So this is, again, time, and this is probing how much europium you have been ejected by neutron stars merger. And all the lines are numerical prediction of neutron star mergers. You see you have three different lines that start at different time here. And this is assuming three different delay time for the time it takes for the stars to eventually coalesce their neutron star. So all the dots are stellar observation, and basically this line is actually not realistic because it assumes a delay time that is too short compared to what you would expect from population synthesis code. So these two lines would be probably the more realistic. But now the question is, how can you explain that so many stars have so much europium before that point? So if you're not able to push this delay time a little bit shorter, to push this line back to be able to collect all these stars, now you can think about, well, I just have to modify my way I see galaxies. What if galaxies in the early universe, at early time right here, was forming stars differently? And this has to do with the star formation efficiency, which is the efficiency to form stars. Well, that's pretty much the same thing, right? But here's the plot. So when you have a bunch of gas and you want to form stars, not all the gas will form stars. Just a little fraction of it will actually form stars. And if you assume that the star formation efficiency is lower, to form the same amount of stars, you will need a bigger gas reservoir. In terms of chemical evolution, that means that you will form the same amount of iron because you still form the same amount of stars, but you will have a bigger gas reservoir and more hydrogen. And therefore, your iron over hydrogen ratio will be different. So to solve this problem, what you can do, that's the same kind of plot, you take this red line, which doesn't fit all this data, and you said, well, let's just say that my galaxy at early time has less star formation efficiency. You increase you increase hydrogen, therefore you dilute your iron concentration and you push everything back toward that direction to have this orange line. And now you can say, well, victory, I now understand why neutron star mergers can occur at this early time. It creates the illusion that neutron star mergers are happening earlier, but you just have changed the way galaxies are forming stars. So that's all great. You publish papers and all that, and people are very happy. And then 2 years later, there's some guy that enters the room and said, hey, I hope I don't disturb. But by the way, neutron stars are actually a little bit more massive than previously expected. Have a nice day. And actually, that is quite a big problem, because if this is true, that means that the amount of iron that is ejected by stars is less. And if this is true, that means that you're going to enrich your gas less rapidly in iron. And this is going to give the exact same phenomena. So because you will eject less iron instead of having a bigger hydrogen, you will create the same process. So all the lines are going to be shifted that way. And now it doesn't need to imply that galaxies form stars differently at the early universe. On top of that, you're going to change that axis as well. Europium over hydrogen. Then you reduce iron. Sorry, I said it wrong. Europium over iron. If you reduce iron, everything goes up. And then you see, whoa, I have way too much europium, but that's okay because you have a parameter in your galaxy model that is named number of neutron star mergers. So you just reduce that and you recover the same fit. And just that, it has changed your interpretation of how many neutron star mergers you need to fit the observations. If that is not confusing enough, you also have galactic inflows and outflows, and depending on how these processes are occurring in the galaxy, you will add more or less hydrogen, expel more or less iron, and then you will be able to create this sort of shift again. So the bottom line is, in this field, there's a ton of degeneracy. It is pretty complicated to make sure that we have the right interpretation. So all the physics that goes behind trying to find this plot and explain the observation, you need to know how efficient you form stars, what is the gas circulation inside your galaxy, how much iron is ejected by your stars, and what is the rate of neutron star mergers, which is typically given by population synthesis code, here by Chris Belzinski, who many of you knows already. And the mass function of black holes and the relation between the initial mass and the final mass of stars is actually an input for these model and for these model. So for now, there's a lot of uncertainties, and we don't actually know what is that relation. And if we have a better constraint on this, or if we realize that these value needs to be changed, well, we have to recalibrate everything about the way we evolve our galaxies. So as I said, there's a lot of degeneracy, and to be able to move forward with this, we need to break the degeneracy. So we have made a test with our galaxy model, and we found that using a Markov chain Monte Carlo code, there's quite a degeneracy between the inflow rate and the outflow rate, because they can modify the iron concentration in a very similar way. So we need to break that, and I want to make a little parallel with what's going on in the microlensing area. If you want to know the mass of the lens and the distance of the lens, and you are using, for example, the Einstein radius in terms of angular, in terms of your angle, you have quite a lot of degeneracy, actually, because you're measuring the distance and the mass at the same time. So you need to use different type of constraint to have different lines and find the intersection, which is the best solution. So I basically need to do this with my model. I can include, for example, observation, hydrodynamic simulation, create different lines, and pick the value that it would be right at the intersection. So I need to do this, but I need to do this, well, the community, not just me, but we need to break the degeneracy at all scale. And again, WFIRST and having a better understanding of what is the distribution of the mass of neutron stars and black hole is going to help a lot constraining this stellar model. And as you can see from this plot, everything that is happening in the world of galaxy evolution and the evolution of the element sits on stellar models. So that is quite the foundation. Okay, so as a conclusion, so if we want to understand stars, galaxy, and how they evolve, we of course need to break the degeneracy, and the stellar models, as I said, are clearly the foundation. Microlensing can help in deriving this mass function that is currently missing. And of course, I just want to say that this field is nice because it's going to bring a more coherent picture of the evolution of stars and galaxies and all that. And I'm not going to lie, WFIRST and microlensing is not going to solve everything, but it's going to help and add additional constraint, because the bottom line is any additional constraint will help in getting us closer to the real picture, and it will prevent us from going in direction where we will have the wrong interpretation about how galaxies are evolving. And if you're ever interested in the evolution of galaxies and chemical evolution, we have a pipeline that is open source here on GitHub. Do a little bit of advertisement but we can play with stellar models and the galaxy evolution models. We have teaching notebooks. So it's all ready for you to use, and you just download the code and you have some instruction about how to play with these things if you're interested. So that's it for me. Actually, I'm not. I did not do this this work particularly, but I'm pretty sure they took something pretty classical. I think they must have taken the initial mass of Pavel Krupa or something like that. Yeah. Right. Yeah. It's clearly. Oh yeah. Of course. Yes. Yeah. Yeah, exactly. People use saltpeter, I guess mainly because it's already in their code and that's how it is. But yeah, and I didn't talk about the initial mass function, but there are also uncertainties coming from there because the initial mass function tells you how many massive stars you have compared to low mass stars. And if you change this ratio, you're going to change, obviously, again, how much iron in total you're ejecting. And yeah, exactly. Well, it's hard to observe stars in the bulge because there's so many things on the way. And but if using you mean by microlensing, you could enhance the signal and have a, yeah, that.
It's been done for a few tens of events. There is a proposal to do it for thousands of events.
That would be fantastic, yeah, because we know, so the galaxy, for now I just put all the stars in the same plot, but the bulge, the disk, and the halo has a very different formation history, and the chemical abundance in star can actually track these different star formation histories. So we know that the bulge has a different chemistry than the disk star, but I don't think we have enough stars in the bulge to make a strong conclusion about yeah, that would be fantastic. Right, that's a pretty good question. So it depends on which model you use. So for example, the model that I've shown is only like one line. It's a pretty simple model where you say, oh, well, here's my volume of gas. It's all homogenized. And so you don't keep track of where things are actually occurring. But if you use something like a hydro simulation, this can be quite important because if you assume that there is a kick, that means that the europium will not be ejected where the stars are forming. So you can eject europium randomly somewhere in space, and then this is going to make the analysis of stellar abundance quite more complicated.
I guess I mean more, what about scientific velocity?
Oh, right. You know, I'm not sure about this, but I would say that as long as they go through the line of sight, it'll be fine, I guess. I'm not sure how that will, yeah. I mean, they will surely receive some kick, so they will go somewhere else. But I think that could be problematic, for example, if the kick is sufficiently large and it's going perpendicular to the disk, so maybe they're just going to be free floating in the halo and it would not go back inside the disk, so maybe you will not detect them in this situation. I don't know if it answers your question a little bit. Oh, it's quite unsure right now, but it can be, well, it depends on who you are asking, but I would say like maybe it can be as high, I would say in between 10 kilometers per second to 500 kilometers per second. I will give a big range because I'm not exactly sure the exact number, but it can be significant. Actually, that's kind of, oh man, I don't know that. What is that unit? Oh yeah, absolutely, yes. I don't know how it relates on the arc second, but this is actually I mean, that's kind of it's not on average 500. I mean, I know it can go as far as, but most of them are going a lot slower. But I know that in dwarf galaxy, the kick is typically higher than the escape velocity of that galaxy. So. Right, okay. Well, honestly, I need to revise this number. I didn't know that this was going to be become a serious conversation. Please, I will check the number. But yeah, I know it can be relatively fast. Yeah, so I'm not sure if there are a mass derivation from pulsar. That's something I don't know, but from X-ray binaries, at least people can derive mass, and they are always lower mass than black hole. That's for sure. Is that a question or? Oh. Yes. This.
So what do you do about that area?
Oh, you mean what do I do with this pink line?
Yeah. So I understand that these black lines higher are observations. Right?
Yes, and these are models.
Not observe anything in the middle.
Right.
Why?
Well, that's a good reason why I don't. This is. You mean why in terms of stellar evolution? Or you mean why we don't see this? Why there's no actually object in this gap?
Yeah, why we don't see it and the model predicts it?
Oh well, you mean these one? Well, these one are because it depends on your on the initial mass to final mass relation that you assume. So, for example, if you have, let's be imaginative a little bit. So, if you have the final mass, initial mass. So, if you are to derive this pink line, you assume that the initial mass is kind of growing constantly. So, you will kind of always create some sort of remnant depending on each of the mass. But if you use the red line, the remnant mass is actually kind of flat, and then at some point there's a big jump where you become in the black hole area. So there's no region in the star where you're going to produce these.
Okay, so this mass is just lost during the birth of neutron star or black hole?
It's just what?
Is it just lost during the birth of the black hole?
Oh no, it's just never formed. So you just never having started or ending with this mass. Like you're always either forming neutron star with these mass, or for some reason you're just going to form big black holes. And I don't know exactly the reason why this is a thing theoretically, but I know it was motivated by this. And these lines, blue and pink, are alternative models that NeuroGrid think is not going to do it because it's not respecting the gap. But depending on your assumption regarding the initial to final mass, you have either this gap or not. Okay, good. I hope. I heard this in my talk. Well, probably this is nonsense. Good.